Hi, mechanics friends. Now we're ready for our final example of this lesson. So in this example, we have a 12-inch by 12-inch concrete column that's subjected to multiple loads, right? So we see we have a 5-kip load, a 10-kip load, and then we have an axial compression load of 1440 kips. We are asked to calculate the magnitude of the normal stress at points A and B in the cross-section shown. So let's take a look at a physical model of this 12-inch by 12-inch column and see how the forces applied are affecting points A and points B in the cross-section. All right, so the first force we want to examine is the 5-kip force in the negative Z direction. And so if we go ahead and we take that 5-kip force and we apply it, we'll see that it's going to cause the column to bend, and it's going to cause the column to bend about the y-axis. And as it bends, we see that we get tension along the backside and then compression on the inside. So down here at points A and B, we see that this force causes compression at both points A and points B. Let's do the same for the 10-kip force. The 10-kip force is being applied in the negative y direction. As we apply this force, the column bends in this manner. And in fact, it's bending about now the z-axis. As we do this, we see we get compression along this inside face and then tension along the back. So when we think about points A and B in the cross-section, we see that A here, it happens to be on the compression side because it's on the inside here. And we see point B is on the back side, and so it's experiencing tension. So we see the 10-kip force causes compression at A and tension at B. Lastly, we have our big 1440 kip force, and that's acting in the negative x direction. And so that's just compressing this column, and so it acts as a force over our whole column. And you can see that that force will compress the entire cross-section, and we'll see that we'll end up with compression at both points A and B due to the 1440 kip load. All right, so that's a physical look at what's happening in this problem. So let's go ahead and finish those calculations. As we saw in the demonstration, we had the different loads producing different effects at points A and B. So I just want to go ahead and put those into our notes. I really want you to focus on the behavior of what's happening A and B due to these loads. I think being able to quickly identify the depending upon which way the loads are acting, whether or not it's causing tension or compression at A and B is a very important skill. So we said that for the 5-kip load that was acting in the negative Z direction, that was causing compression at both points A and B. And I'll just denote that this is bending compression, right? So this is compression due to bending, which is going to be tied back to our bending stress equation, my over I. The 10-kip load acting in the negative y direction, that causes compression at A, but it's causing bending tension at B. So we see just the orientation of the load and where the points are in the cross-section, that due to bending, A was on the inside of the column as it was bending, so it got axial compression. And then B was on the outer edge, on the back fiber, that was in tension. Finally, we look at that 1440 kip load. That one's causing axial compression at all points in the cross-section. So at points A and B, or any of the other points along that green square at the bottom. Now the difference between bending compression is going to be tied back to our my over I equation. But the axial compression, the 1440 kips, I think we hopefully recognize being able to calculate that compression from P over A that we did at the beginning of the year. Because we're going to have both my over I and p over a in this problem, it'd probably be prudent to get those values from our cross-section. So I'm just going to go ahead and label points A and B on this little cross-section and draw my y and z axis in there. All right, so when we take a look at the 5 kip load that's acting in the negative z direction, we see that it causes a moment about the y-axis, and that's what we said from the demonstration. So it's causing bending about the y-axis. The moment that it causes is the force times the distance from the y-axis, which in this case is going to be 15 feet, or I'm going to convert that into inches so that it's 180 inches. So 5 kips times 180 inches. So that's going to give us a total moment of 900 kip inches. I'll repeat this process for the 10 kip load. So the 10 kip load we said was bending about the z-axis, causes bending about the z-axis. What that means is, on that cross-section AB, that the z-axis is our neutral axis. So the moment about the z-axis is 10 kips times 180 inches, or 1800 kip inches. Finally, we look at the compression. The compression we said was going to be related to P over A, so we just need to know what P is. P is going to be 1440 kips in compression, pushing down on that cross-section. All right, so as I said before, we want to get the properties of this column cross-section. So when we're thinking about moment about the y-axis, this is our distance z, and that'll be like our distance z to both points A and B. And that distance is going to be 6 inches. Likewise, for the 10 kip load that causes bending about the z-axis, we're going to need the distance, and this distance we'll say is the distance y. Y to point B is 6 inches, and then A is 6 inches. Now, we have a square cross-section, so all of these distances were 6 inches. But we could easily apply this to a rectangular cross-section, in which case y and z would have different values. Next, we'll calculate moment of inertia. Moment of inertia about the y-axis is going to be 1/12 base times height cubed. The base for the y-axis is going to be 12 inches, and then the height is going to be perpendicular to the y-axis, or the 12 inches that I underlined in green. So 1/12 base times height cubed. So doing our calculations, that gives us 1,728 inches to the fourth. Likewise, we're going to need to know what's happening about the z-axis. Now, because it's a square, it's going to have the same answers. But again, if I wanted to look at this as a tube, I would have to switch my base and my height. So my base for moment of inertia about the z-axis would be the 12 that's underlined in green, and then the height would be the 12 underlined in red cubed. So it results in the same answer, but again, I just wanted to kind of show you how you would apply this to maybe a rectangular cross-section. Finally, we need our area. Area is just going to be base times height, so that's 144 inches squared. So I think we have everything to go ahead and calculate the stresses that are occurring at both points A and B. Alright, so I'm going to go ahead and add a rectangle box to the top of this page so that you can come back to this and check out this formula. This is going to be the first time that we've combined stresses. So we have a whole lesson a little bit later in the semester where we're going to look at combined stresses. But you can see here that I have at points A and B, I had both bending stresses and axial stresses from axial force. So that gives us the general equation for normal stress, which is going to be sigma equals P over A plus my over I. So you'll hear a lot of engineers talk about this. We'll talk about P over A plus my over I. So what we're talking about is some effect of axial force, P over A, plus some bending stress caused by the bending moment times y over the moment of inertia I. So let's take a look at those stresses at A. If I do P over A, I see that I have 1440 kips divided by 144 inches squared. And again, I'm going to take tension as positive, compression as negative, and I'm using the problem figure to determine whether or not these are plus or minus based on how I said on the previous page if it was going to cause compression or tension. So you can see that for P over A, I've given a negative sign for compression. Next, we have the effect of the 5 kip load. That gave us a moment of 900 kip inches. We said the distance from the y-axis to point A was 6 inches, or that distance z. And then we divide it by I, the moment of inertia about the y-axis, 1728 inches to the fourth. Again, we said this was caused compression, so I've given it a negative. And then we repeat that for the 10 kip load. For the 10 kip load, we have 1800 kip inches times a distance, 6 inches, divided by 1728 inches to the fourth. This time, the moment of inertia is the moment of inertia about the z-axis. As I've been mentioning in my narration, I've been applying negative signs just because it causes compression. And so I'm just going to make a note of that here in this calculation. So for sigma A, I go ahead and do some multiplication and division, and I solve that sigma A is equal to negative 19.375 KSI. The negative sign tells me it's in compression, and so I've labeled it accordingly. So let's take a look at the stresses at B. If you want to give stresses at B a try, go ahead. You can pause the video and give it a try. But if not, here we go. So again, we have at B, we have the negative P over A load because the 1440 kips causes compression everywhere. And this time I'm going to write it out in variable form. Next, we have the moment about the y-axis, which was caused by the 5 kip loading, times the distance to B divided by the moment of inertia about the y-axis. We said that the 5 kip load caused compression at B, so I've assigned a negative sign. Finally, the 10 kip load caused a moment about the z-axis, and then we have to multiply by the distance from the z-axis, which is in the y direction, so that's what I've called yb. And then I have to divide by the moment of inertia about the z-axis. I've given this a plus sign because this 10 kip force we said caused tension at B. And so I've added plus for tension, negative for compression. Alright, so I'm going to plug in my values. I get negative 1440 kips over 144 inches squared for my P over A term. Then I get a negative 900 kip inches times a distance of 6 inches to point B divided by 1728 inches to the fourth. Then I get a plus 1800 kip inches times the distance yb that I labeled on the previous page, which is also 6 inches, divided by 1728 inches to the fourth. And so I see that doing my math, the stress at B in this case is a negative 6.875 KSI, Negative still implies compression, but we note that B is in less compression than A because of the tension caused by the 10 kips loading. So in this case, A is kind of a more critical spot than B. So the last step in the design process would be to check points A and B using some sort of failure criterion like Tresker or von Mises to predict whether or not we would expect failure to occur. Well, I hope you enjoyed this lesson and that you're expanding your mechanics knowledge to be as vast as the oceans. Or at least you're better able to apply our bending stress formula, sigma equals my over I.